All right, welcome. Today we're pulling back the curtain and taking a peek under the hood of our computers. We're going to explore the secret kitchen that lets your machine juggle, a dozen different things at once without even breaking a sweat. So let's step inside and see how all this magic really happens.
Really think about that for a second. You've probably got music playing right now, a bunch of browser tabs open, maybe a game minimized. How is it all happening at the exact same time? It really does feel like some kind of sorcery. But I promise you, it's actually just a masterpiece of organization.
And here's the secret. The best way to understand it is to think of your computer's operating system, your OS, as the head chef of a huge, super busy restaurant kitchen. This chef is in charge of everything, taking all the orders, managing the entire staff, and making sure every single dish goes out perfectly and right on time.
So our first stop in this crazy kitchen is to get one thing straight: the difference between a recipe and the actual dish that's being cooked. This is like the most fundamental idea we need to grasp: the difference between a program and a process.
This breaks it down perfectly. A program, think Spotify or Chrome, is just a passive set of instructions sitting there on your hard drive. It's basically a recipe book on a shelf, not doing anything. But the moment you double-click that icon, the head chef, the OS, grabs that recipe, brings it into the kitchen, gives it to a chef, and they start cooking. That active thing is a process. The recipe is now a dish in the making.
And that's why a process is so much more than just the program's code. You gotta think of it as this living, breathing entity. The OS sets it up with its own little cooking station. It gets memory for temporary data, another space for memory it needs on the fly, and a little marker to keep track of which step of the recipe it's on. It's the whole shebang.
Okay, so our kitchen is now just buzzing with these active dishes, these processes. How on earth does the head chef manage all this activity without it turning into complete and utter chaos? Well, it does it by keeping a very close eye on the state of every single process.
See, a process has its own life cycle, just like an order in the kitchen. First, it's new. The ticket just came in. Then it becomes ready. All the ingredients are chopped and prepped. It's just waiting for a free stove, which is your CPU. Once it gets that stove, it's running. Now, if the chef needs something, like an ingredient from the pantry, it goes into a waiting state. And finally, when the dish is plated and served, the process is terminated. Done.
But with dozens of dishes all in these different states, how does the head chef possibly keep track of it all? Easy, with a clipboard. A separate clipboard for every single order. And in the OS world, this clipboard has a name: the Process Control Block, or PCB. And this clipboard is just packed with all the vital stats. The PCB stores everything the OS needs to know. What's its current state? What's the very next instruction it needs to run? What memory is it using? This is absolutely crucial because it lets the OS instantly pause one process, save everything about it to this clipboard, and then switch to another one. That super fast swap is called a context switch, and it's what creates that amazing illusion that everything is happening at once.
Now, this system is great for individual chefs working on their own dishes. But a real kitchen isn't silent. Chefs need to coordinate. What if one chef needs the sauce that another one just finished making? This is where something called inter-process communication, or IPC, comes into play.
So there are pretty much two ways for these processes to talk. First up is shared memory. The best way to think of this is a common cutting board. One chef can chop up a bunch of vegetables and just leave them there for another chef to grab. It's incredibly fast, but you can imagine the problem, right? The chefs have to be really careful not to get in each other's way. The other way is message passing. This is literally just shouting across the kitchen. It's a bit slower, but it's much safer because the head chef, the OS, acts like a moderator, making sure the message gets delivered properly.
Okay, so up to now, we've mostly pictured one chef per dish. But some dishes are ridiculously complex. A simple steak is one thing, but what if the order is for a 5-course tasting menu? This brings us to the next level of kitchen efficiency: threads.
Seriously, just imagine it. One chef trying to grill the meat, whip up the sauce, perfectly plate the vegetables, and create some fancy garnish all at the same time. It would be painfully slow. It's not going to work. There has to be a better way.
And that better way is a thread. You can think of a thread as a specialist assistant chef who works inside the same process on the same complex order. So now you have a grill specialist, a sauce specialist, and a plating expert. They all share the same kitchen station and the same ingredients. That's the process's memory. But they each have their own specific task. And now preparing that complex dish becomes way faster. And the benefits of this teamwork approach are just huge. It means your app stays responsive. If one thread is busy saving a big file, another thread can keep the user interface running smoothly so it doesn't freeze. They automatically share resources, which is super efficient, and this is a big one, it's way cheaper and faster for the OS to manage these little assistant chefs than it is to set up a whole new kitchen for a brand new head chef. This is why pretty much every modern app you use is multi-threaded. Now, this idea of threads working together brings us to a really important and sometimes kind of confusing distinction. And that's the difference between juggling a lot of things at once and actually doing a lot of things at once. This is concurrency versus parallelism.
Okay, let's break this down. Concurrency is like having one amazing chef who's managing 10 different pots on a single stove. They're constantly switching between them, a little stir here, a taste there, so that all the pots are making progress over time. It gives the illusion of multitasking. Parallelism, on the other hand, is having multiple chefs and each one has their own stove. They are actually cooking multiple things at the exact same time. And this is only possible if your computer has a multi-core processor.
All right, I know this might all seem a little abstract, but trust me, it has a massive impact on how you use your computer every single day. And the perfect example is probably the web browser you're using to watch this right now.
Modern browsers like Chrome are basically designed like a perfectly run restaurant chain. You've got the main browser process. That's the restaurant manager handling the main window and menus. But here's the genius part. It then creates a totally separate process, a separate chef in a separate kitchen for every single tab you open. The brilliance of this is that if one chef totally botches an order and their kitchen catches on fire, in other words, a single tab crashes, it doesn't burn down the whole restaurant. You just close that one tab and the rest of your browser keeps chugging along just fine. It's the power of process isolation in action.
So there we have it. We've seen how the OS is this master chef, managing processes like individual dishes and threads like teams of specialists. It's this beautiful dance between isolation and cooperation that gets an incredible amount of work done. Which it leads to one last thought. If a process is a chef and threads are their assistants, how does the OS manage the pantry? How does it handle giving them a seemingly infinite supply of ingredients? Well, that gets into the magic of memory management, and that's a story for another time. Thanks for joining me in the kitchen.